We will study introduction to the standing waves. So first, let's see the term of interference for a string that is closed or attached to one end. So here we have a string. Here it is attached, and from here we are producing a wave. So what's going to happen is here is coming the wave, something like this, and when it comes here, then actually you can try it. When we see that the wave is coming back, we will see the reflection of the wave. Here is the reflection of the wave, and it's coming in the opposite direction. So direction here I'm talking about right or left. So opposite direction and opposite displacement also. Here remember that in a wave we are talking about the displacement of the particles of the medium. So the displacement here is on the y direction, here is positive, and when the wave is reflected it's coming on the negative direction. So we have opposite direction and opposite displacement. If we now have a string that is attached here at the end to a ring that is surrounded this bar without friction, when we do this, yes, we are generating a wave that is advancing, something like this, and when it comes here, then it would be at the maximum here. If you see here, when it hit it, oh sorry, let me put it. When it hit it, the extreme, it is at 0, and then it comes back reflecting. Here, when it hit here, is at the maximum. Here is at the maximum, and when it comes reflected, here is going in the opposite direction, is now going to the left. So now opposite direction, and the direction of the displacement is the same. So the same displacement, or the direction of the displacement. So now let's see the interference. These waves are called traveling waves. Traveling waves, because yes, this is a wave, and not all the particles are moving at the same harmonic motion. Alright, now let's see now the interference. Usually, or in general, interference is what happens when two or more than two, greater than or equal to two waves are passing through like this at the same moment. They have the same speed, the same frequency, but different amplitudes. And the amplitudes could be on the different direction. For example, here I have a wave that is coming like this, and I have here another wave that is, let's say, coming like this. So as you can see, this is similar to the previous example that we had here, when this extreme was attached, and we have the reflection of the wave that is coming on the opposite direction and the opposite direction of the displacement. So here we have that the same example, and now when these waves are passing through, yes, we will see that here when they meet together, we will see a resultant wave that would be, for example, something, I think that in this case would be something like this, because this has a larger amplitude than this, something like this, and then they will continue as they come before. So this wave now will be here, and this wave now will be here. So then it goes as if nothing will happen. And now we can have again two waves coming here, one going on this direction and the other on this direction. So this is similar to this example. We have that they go on different directions, but the direction of the displacement on the y-axis is the same. So here we will have a resultant wave. Here, for example, it would be something like this, and this because the amplitude are coming up. This is constructive interference. The previous example was the destructive interference. So this is when we have just one extreme is closed, or here we have that both waves are coming. Next, we will see here when we have a string and is attached on one end, it will produce a sound here, or a movement of the wave many times. We can produce now the standing wave. The standing wave is when there is no motion or displacement of the wave, like this. So this particle will be moving up and down, so we will have displacement, but the wave will not be moving. So here we use this, and we will see something like this, the wave, like this, but there is no propagation of the wave. So there are points, for example, there are points at which there is no movement of the particle, there is no movement, and because there is no movement, the displacement is 0. So we have y of x and t equals 0. And we have other points at which the amplitude here is the maximum. When we have no movement, this will be called a node, and when we have the maximum amplitude, it is a antinode. So in the nodes we have displacement 0. In the antinode we have displacement of actually would be the maximum. So now in the wave example that we have the when we saw the interference, we saw two waves approaching. Those waves, we will return to this in a while. Those waves, this and this, for example, whatever it be, they have the form of y equals to x, y of x and t equals to, let's say, a times the cosine of kx minus omega t. Let me call that this describes the wave that is going to the right, and like this. And the other one would be y sub 2 of x and t equals negative a cosine of kx plus omega t, because this wave is reflected on the opposite direction of the displacement. So here I have this negative, and coming towards the other side on the x direction, so here I have this change in sign. So the resultant wave that is going to be formed is the summation of these two. Actually, this is called the superposition principle, and so we have that y is equal to y1 plus y sub 2, and this is, if I add these two, I would have a times here I can factor this as remember the identity of the cosine. Remember, cosine of a plus b is equal to cosine a cosine b minus sine a sine b. So here I would have a times the cosine of kx cosine of omega t plus sine of kx plus, times sine of omega t, and I will add this to negative a times cosine of kx cosine of omega t minus sine of kx sine of omega t. So here I will have this. I'm subtracting one to the other because one is going to this direction and the other is in this direction. So I have this minus this. I will have 2. First, let me see. I have cosine of kx cosine of omega t, a and minus a. So this both will cancel. And here I have, sorry, I think that in a moment I said subtracting, but I mean I'm adding. And here I have a sine of kx sine of omega t, and this is sine minus this is positive, so actually I have that y is equal to 2a sine of kx sine of omega t. Now I did this like this, and it depends on how you hold the wave equation, because you can have it as a cosine of kx minus omega t, or you can put it as a sine of kx minus omega t, and so you will have here a cosine instead. Actually we can do it also, but here the important issue is that this now is the equation of this new wave that was formed, and this does not have the form of the argument that is x plus or minus omega t or something like that. We don't have this, and so this does not represent a traveling wave. This is a wave that is standing. It's a standing wave. At any different time, all the waves are moving to the same, and all the particles are moving to the same time. So this is the amplitude. This is the amplitude, and if you see, okay, in a sense, also the amplitude is twice the maximum amplitude is when sine x is 1, is 2a, and this is twice the amplitude of one of the waves, because we have here one and here another. So we also have that now we have this wave that is moving, but it is not propagating, and so we have the nodes, the antinodes, and if we want to find the nodes, we have this needs to be equal to 0, that is y of this is equal to 0 when we are at the nodes. So it doesn't matter at which time we are talking, these nodes will never move. So the only factor that determines this is the position of the particles. This particle is a node, this is a node, or the particles that are here. So is this what determines if it is a node or antinode or neither? So if I want to find the nodes where there is no movement, I have that sine of kx is equal to 0. So I have kx is equal to 0 by p, 2p, 3p, etc. And so I have x is equal to 0, p over k, 2p over k, 3p over k, and remember that k is the linear wave number, that is 2p divided by lambda. So here I will have x is equal to 0, p divided by this is k, so 2p lambda, so it is p divided by 2p, lambda, then I will put this here, and I have lambda over 2. So lambda over 2, 2 lambda over 2, 3 lambda over 2, etc. So these are the x's, these are the positions at which we have the nodes. And if you see, they are half wavelength apart. And this fixed end is a node. This fixed end, or well, actually, if you want, let me put it here to see it better. This fixed end is x equals 0, because here I'm beginning. And then I have all these nodes. And the antinode is when we have the maximum amplitude, that is when sine of kx is plus or minus 1, plus or positive or negative 1. So I have that kx is pi p over 2, 3 halves of p, 5 halves of p, etc. So I have that x is 3 halves of p over k, or 5th half of, sorry, 1 half first, 3 halves of p over k, 5 halves of p over k, etc. So x is equal to lambda over 4, 3 lambda over 4, etc. So again, 5 over. So we have that the nodes. The first node is at 0. The second is at lambda over 2. So here, let's say here is lambda over 2. Then 2 over 2 lambda, 3 over 2 lambda. So the distance between a node and another is half the wavelength. Now on the antinodes I have 1 at lambda over 4, so I have 1 here. Then another at 3 for lambda here, 5 for lambda here. So again, between the antinode and the adjacent antinode we are half wavelength apart, but between the first antinode, well, between a node and the antinode we have 1/4 of wavelength apart. So this is getting very, very extensive. So in the next video we will talk about what happens when we have both extremes of the string attached.